Today, we will be talking about Spectral Science's SBIR program called Full Trajectory Aero-Thermo-Mechanical Coupling for Hypersonic Flight. This work came out of an SBIR topic from Navy SSP. The work presented here was compiled by Dr. Alexandra Woldman, the principal investigator for this SBIR contract, but many others at Spectral Sciences have helped support the technical work discussed herein. So, let me tell you a little bit about Spectral Sciences, who we are, and why we are well suited to do this work. Spectral Sciences is a nationally recognized resource hub for expertise in spectroscopy, remote sensing and imaging, combustion and propulsion technology, radiative transfer processes, and most recently, hypersonics. We have 40 years of experience working with the U.S. government, prime contractors, and private industry. On top of that, we are 100% employee-owned. Spectral Sciences has several software success stories under our belt. Our most successful code, ModTran, is a radiative transfer code developed through a collaboration with AFRL and with SBIR funding. It is used widely in operational and research sensor and data processing systems, including by the U.S. government and prime contractors. We also distribute Quack and Flash, two atmospheric correction codes, which are sold as part of ENVI by Harris Geospatial Solutions. Spectral Sciences is staffed with 33 scientists and engineers, most with advanced degrees, with a wide array of expertise. Our staff has recently grown in the area of hypersonic simulation and modeling, with more growth expected in that field in the coming years. Our work is research and development focused, and we have excellent relationships with academics in our areas of work. For this specific program, Spectral Sciences is addressing an inefficiency in the Navy's simulation and modeling suite for hypersonics. The challenge in modeling hypersonic vehicles is that they operate in an extreme environment, where the fluid and solid response are highly coupled. High-fidelity modeling exists for both structural response and computational fluid dynamics, but mapping interface data between disparate codes is error-prone and difficult. This leads to engineers needing to use limited coupling, and thus incomplete data, to model critical points along a trajectory. Our objective for this program is to develop an automated high-fidelity modeling and simulation software that will allow users to accurately model the highly coupled physics associated with aerothermal flow, high-temperature material response, and thermal protection system for hypersonic vehicles over a full trajectory. We then hope to transition this technology to the U.S. Navy and other DoD partners. By the end of Phase 2, we aspire to have a prototype simulation tool that allows co-simulation of coupled thermoelastic finite element analysis and computational fluid dynamics for a hypersonic flight vehicle over a full trajectory. So, continuing into the details of the issue, some of the most needed improvements for coupling this aero-thermo-mechanical response over a full trajectory are the following: mapping back and forth between computational fluid dynamics and finite element solutions over the course of trajectory, automation of the aforementioned mapping, trajectory traversal automation, and providing a specific up-down survivability assessment for trajectory. Right now, Navy analysts are selecting individual points along trajectory for analysis and manually mapping results between high-fidelity tools. Our software tools will automate this process and remove the requirement to select points, instead simulating full trajectory. Beyond the predictive modeling we can provide for specific vehicle and trajectories, other applications for this could include analysis of hypersonic vehicle flight tests and ground tests, design and analysis of scramjet inlets and nozzles, or other hot deformable features, and infrared signature prediction for tracking, defense, or flight test analysis. I'll now review the coupling framework we have developed for this specific program. For this work, we have built our entire framework around the computational fluid dynamics software called US3D, which was developed at and is owned by the University of Minnesota and is distributed by Virtus Aero. We have a great familiarity with this tool, which is widely considered state-of-the-art for modeling hypersonic flows, and its plug-in architecture allows us to develop tools that seamlessly hook into the software. For our finite element software, we have selected Abacus. Other finite element tools could be used in place of Abacus in future expansion and development of this framework, but Abacus is a well-known and well-regarded software that is available on most government computing systems, including the DoD high-performance computer clusters. We use two main plugins for US 3D to power our coupling framework: the Trajectory, Ablation, and Shape Change plugin, and the coupled hypersonic Aero-Thermal Solid Modeling plugin. The first manages the trajectory traversal and guides the coupling frequency, while the second is the main communication tool between the fluid and the solid solution, sending data back and forth between the two software, as indicated by the yellow arrows in the figure below. We utilize Abacus Python scripting for building and running the finite element model in Abacus, as this allows us to work entirely from scripts without launching any graphic user interfaces. We have developed an innovative co-simulation structure that allows both US 3D and Abacus to run simultaneously, waiting for signals and communications from one another to start and stop simulations at predetermined coupling points as we march along in time through the trajectory. This is done through a new, highly efficient binary data passing scheme developed for this program. This capability of launching both simulations and passing data back and forth as we traverse a trajectory has been tested successfully on the DoD supercomputing clusters. On this slide, you can see the progress we have made on this program thus far, and the work we still expect to complete. Notably, we demonstrated the feasibility of our proposed coupling scheme in Phase 1, and have made great progress towards the fully coupled automated prototype development. We are testing our framework on real Navy flight data and expect to have results very soon. By the end of the option period for Phase 2, we hope to provide the Navy with an initial software release for feedback and testing. To review what has been discussed in previous slides, let's just highlight some features of our coupling framework. Our framework couples two validated high-fidelity commercial software tools for computational fluid dynamics and finite element analysis. This is valuable because there is no question about the quality of the results produced by the base software, assuming the user provides high-quality inputs. There is also documentation for these underlying tools, as well as an existing user base. Our framework will automatically map interface data between high-fidelity computational fluid dynamics and finite element solutions. This means that the user does not have to manually map or interpolate any data, but merely provide the correct inputs to launch the simulation. This will be significantly less error-prone and much faster than the legacy methods. Our framework will automatically traverse the entire trajectory for a vehicle flights. This means the effects of time history will be accounted for, providing a higher quality solution of the vehicle heating. The analyst will no longer need to choose points of interest along the trajectory to probe the solution, as the entire trajectory is analyzed. This will take the guesswork out of choosing analysis points. Finally, our framework will provide a straightforward survivability assessment for the vehicle for a given trajectory. This will simplify decision-making for design and analysis and provide a clear picture of any pain points in either the trajectory and/or on specific locations in the aeroshell that need to be addressed to avoid catastrophic vehicle failure. Our commercialization plan for this program revolves around follow-on work from government stakeholders to help improve and expand the simulation suite. At the end of Phase 2 option, we expect to have a prototype coupling software that couples US 3D and Abacus. Our transition will first focus on including this software as part of the JANF distribution of US 3D Plumewake Hypersonic Toolkit, which is distributed by Spectral Sciences. This is the easiest avenue to provide our tool to users who already have familiarity with US 3D and build interest in the product. We also would love to continue our partnership with the Navy, specifically with the team at Navy SSP. This could include follow-on work to expand the framework, or new test cases around which we can test and perfect our products. Long-term, we would love to expand our market to include other DoD partners, like Army, Air Force, NASA, and DARPA, as well as primes and commercial aerospace companies. But as I said, we expect that any transition of this technology will require follow-on funding, likely from DoD. Due to the nature of the work and the security risks involved, we do not wish to market this work widely. Ideally, follow-on funding would allow us to test against real data, perform validation and verification, develop additional features, code harden, and further automate and streamline the codebase. We expect that the Navy has a vested interest in continuing this work and hope to keep working with them, testing new cases, including flight and ground tests. Thank you for listening to this talk. Again, this technology is being developed at Spectral Sciences, Inc. in Burlington, Massachusetts. If you have any questions about this technology, please feel free to contact Dr. Alexandra Woldman directly. If you have data that we could test in our framework and you want to work with us, please come talk to us. We can work on CUI and classified data. Thank you for your time.